And welcome Calculus 2 students. We are covering derivatives with our polar coordinates. We will see that our derivative dy with respect to x follows this particular formula here, and that has to do with the fact that of how x and y are defined, and the proof of that is in the text. What we're going to do is use the theorem in the interest of time, and we need to find the slope of the tangent line to the following circle. So we would like dy over dx, and with that we're going to need to know the derivative of our function with respect to theta here, and this was going to be 0, and that's all we're going to need for this one. Okay, so let's plop all this in here. I'm going to have 0 times sine theta plus the value of my function, and that would be 10, times cosine theta. Then I need the derivative again, that's 0 times cosine theta, and then minus, and that would be 10 sine theta. Simplifying this, you get negative cotangent theta. So that would be the slope of the tangent lines at any point along the curve. So let's look at our next one. In this next one, we're given a function r equals 1 minus cosine theta, and we would like to know where we have vertical or horizontal tangent lines. Alright, so let's look to see where we might have these vertical or horizontal tangent lines. So I need to look at the slope and see what happens with this slope. So let's do dy over dx. I'm going to need to know the derivative of this. So the derivative f prime f theta is going to equal sine theta. So I'll just go ahead and write all that in. Here we are, having plugged all of that in. I'm going to do some manipulating of this algebraically, and I've got a sine squared here. I'm going to replace that sine squared. Since I have a lot of cosines on top, I'll replace it with 1 minus cosine squared, and just use some trig identities to see if I can make this simplify a little better, because I'd like to have it in terms of factors if I'm going to find where this thing equals 0 or fails to exist. Alright, after a bunch of algebra, this is what I get. The horizontal tangent lines are going to occur when the numerator is 0 and the denominator is non-zero. So let's figure out where this numerator right here is equal to 0. And you're going to need to remember your limits there, what theta varies between. It varies from negative pi to pi, so we'll make sure that we stay within that. We're going to need to look at each of these terms to see where each one equals 0. So let's just go ahead and start for our horizontal tangent lines. We need to figure out where this numerator is 0 and where the denominator is non-zero, because any of those points that cancel out won't work for us. So for our first one, where is 1 minus cosine theta equal to 0, and that would be at both 0 and pi and negative pi. We need to see if that is included, and it does include that, so we're going to say plus and minus pi. Then we need to figure out, that's where the numerator equals 0, and also right here this is also going to be at positive negative 2 pi over 3 in solving this for 0 to cosine theta plus 1. We see that the denominator happens to equal 0 because sine theta equals 0 at that same place, so these won't be included in those horizontal tangent points, and so our horizontal tangent points only occur when theta is positive negative 2 pi over 3. So now let's look at our vertical. Oh, hold on. Alright, we about have all of our work done for us on the vertical tangent lines. If I look at what my possibilities are, and I see where the denominator is equal to 0, then, and I forgot to list on here, theta equals, so the 0 is not going to count because the 0 is a place where it is a non-differentiable point, but we will have plus minus pi, and we will also have those values for 2 cosine theta minus 1 equal to 0, and that will be at plus minus pi over 3. Alright, and that concludes this example. Our next example is to find the area under the curve. So we're looking at a 4-leaf rose with this being our polar equation. We have a definition of area. It is given here. So our area is going to be, now we're going to use symmetry for this one. And note that there are 1, 2, 3, 4, 5, 6, 7, 8 of these shapes. So I am just going to evaluate this thing and just for the first half of the petal, and then just say there's 8 of them, and then I will say 1/2, and this is my function, and with the x-axis here, so it's just going to be 2 cosine 2 theta quantity squared d theta. And in making this, my theta, just making this first half of the petal here, my theta ranges from 0 to pi over 4. And now it's just a matter of integrating. Alright, in doing my integration and using a double angle formula, which made this thing integrate nicely, I get that the area under this curve is 2 pi. Alright, in example 4, I've got to figure out the question. First, I'm supposed to find the area of the region inside the circle and inside the cardioid. So this part right here and this part right here, pretty easy to find. I can just use the general equation for area of a circle, and that is area is pi r squared, but I only have half of that, so the area of that little section, we'll call it area 1. This will be 1. We'll say is pi r squared divided by 2, so that means that area is pi over 2. Got that one. Now the next area I'm going to concern myself is these little shapes here, that one and this one. And if I can just get one of them, then I can double it and I'll know that I have the area of both of them. So I have these little crescent shaped regions, and they're in the second and third quadrants. It's bounded by this function, this r equals 1 plus cosine theta, and the y-axis. So what I'm going to need to do is figure out how it is that I'm going to integrate this thing. So let's just call those two crescents A2 if you want, and then we're just going to say we're just going to double it, and it's just going to get both of them at the same time. Let's see, it's just this r equation, which is 1 plus cosine theta quantity squared. Now for finding the area, if you'll remember, I need to take 1/2 of this due to the fact that it is polar coordinates, and I'm integrating with respect to theta. My theta is going from this pi over 2 on down to pi. So let's go from pi over 2 to pi. I'm just going to multiply this thing out and integrate and see what I get. Okay, just squish my numbers there. Now I have this. I'm just going to use that double angle formula again and integrate. Alright, area total for this A question. Let's go ahead and put an A here. Area total is just the sum of those two, so it's pi over 2 plus this 3 pi over 4 minus 2, and combining that you should get 5 pi over 4 minus 2, and that will be your total area. For the B question, we're to find inside the circle and outside that cardioid. Lovely thing to say. Okay, so I could just find the total area of the circle, which it's of radius 1, so I could say that it was area is pi r squared, so that would be pi times 1 minus the area of what's in the purple, and that would be 5 pi over 4 minus 2, and doing my manipulation on this, that would be 2 minus pi over 4, and that would be a great way to go about this. We can also verify that if we want that area, we could say that it was from, I could integrate this thing from, let's say I've got my, that's a circle of radius 1, so that would be a 1 squared minus this bottom function here, which is the 1 plus cosine theta quantity squared d theta. I will need my 1/2 on this, and I'm going to do both the top and the bottom just to make it easier on myself, so I would double it and then just integrate from pi over 2 to pi, so that would be from pi over 2 to pi, and you can see that I'm just getting the area here and then just doubling it. If you do this and go through this integration, you will find that you get 2 minus pi over 4, which would verify that you could get it going about it either way. Example 5 is just to illustrate that finding points of intersection can be a little dicey at times. Usually when we find our points of intersection, we would equate these two. We would say 3 cosine theta equals 1 plus cosine theta. Doing the algebra of this, I get that cosine theta is 1/2, and with this, that would mean that I have an theta equal to positive negative pi over 3 being possible my points for intersection, and that's definitely true. But sometimes there are other points of intersection because of the way the curve is generated. So if you'll notice, as theta increases from 0 to 2 pi, the cardioid is generated counterclockwise beginning at 2, 0. Then it's going to pass through this 0 when theta is equal to pi. And as it increases, then the circle is generated counterclockwise, then beginning at 3, 0. In which case, for the other one, at 3, 0, it's going to go back through here, and it's also going to be at theta equal to pi. So you have like a hidden intersection point of theta equal to pi, and there's no real hard fast rule for finding these. It's just sometimes you have to generate the graph and then look at it and go, okay, did I get all of my points of intersection? In example 6, we are going to use those intersection points that we got in the previous example in order to find the area of each of these different regions. So we're going to find the area of region A, B, and then C. And we'll have to, region C, we'll have to see, I believe that it's just this half moon. It doesn't say that it's also this moon down here, so we're just going to find the area of this little half moon or this little crescent there, and that's it. So let's get started with this. For region A, that's this region here, I am going to look at this guy and say that he is going to be, I see that the outside curve is 3 cosine theta, so that's going to be my 3 cosine theta quantity squared minus that inside line, which is the 1 plus cosine theta. I am going to integrate this from theta equals 0 to pi over 3. So 0 to pi over 3. And then in which case, what I'm going to need to do, oops, I got to square this, it's got to be d theta. This is going to be a 1/2 here. Since I'm just doing it from the 0 to pi over 3, I'll just be getting this section, and I will need to double it. Oh, I looked at this a little closer. It's hard to tell, really, from what they have here, if I'm just supposed to find it in A and they just want the top part of the graph, or do they want the bottom part too? I don't really feel as though they're really specifying here, so let's just find the top half and not double it, and we'll just find this. And we could say that if they wanted us to find the bottom as well, we would just take what we found in A and double it. I'm just going to multiply all of this out and simplify and see what I get for my integral. Alright, for our B section, we're looking at, I probably should do a different color, this part right here, and we could just say that it is this semicircle of radius 3, so the area of B is going to be pi r squared, so that's the radius there is 3 squared divided by 2, because it's just a semicircle, minus this pi over 2, because I'm subtracting out that area of A. So this would be, let's see, that's a 9, then 9 minus 1 is, oops, said that too quickly, that's actually a circle of radius 1.5. Just because it went out to 3 didn't mean it was the radius of 3. So just when it was 1.5. So if I subtract these two, then I would get 5 pi over 8. Now you can go ahead and evaluate the integrals if you want. You'll get the exact same thing, and what you would do is, I'll just set this up for you. Alright, let's see what we've got here. I want the area under the curve from theta equal 0 to pi over 3, and this would be my function I would need to look at, and that function is the 1 plus cosine squared theta. Then I would break that up, and I would get this portion right here, and that portion would be the part from the pi over 3 to pi over 2 here, and that is of 3 cosine theta. Alright, integrate that, you'll still get 5/8. Best just to use symmetry. This next integral will need to be busted apart from this pi over 3 to this pi over 2 here, but notice how this would be the top curve on that, and this one would be the bottom curve on that. But once I got to this pi over 2 all the way to pi, in doing this part, I only have that 1 plus cosine theta and the y-axis, so I'm not going to have that. Be sure and look at your top and your bottom on these. So I'll set up that integral. Okay, so we set up that integral in 2 pieces for this first section from pi over 3 to pi over 2, and it is your top curve minus your bottom. And then the very last part of that was just this little part of the shape there, and it was just that cardioid from the pi over 2 to pi. And when you integrate that, you get pi over 8. And that concludes 11.3. If you have any questions, see me at the Collaborate or give me an email. Thank you.